So, we have seen examples of how we can simplify the Navier-Stokes equations, namely the mass and momentum balances in a Cartesian coordinate system. We have also seen why these equations would be different for other coordinate system, for example, in a cylindrical coordinate system and a spherical coordinate system and so on. And we learned that the main difference is because the unit vectors, okay, that you have for non-Cartesian coordinate systems is location specific, and therefore they give rise to non-trivial terms in the equation, and therefore the equations would indeed look different. So, we can see an example of a cylindrical coordinate system and see how do we simplify the equations, and that flow is a very nice flow because it gives you a lot of other insights into the system. So, this is flow between two concentric cylinders. Okay. So, you have two cylinders, okay, one inner cylinder and one outside cylinder. I am giving the top view. So, let us say that is your inner cylinder and that is your outer cylinder, okay, and let us say Ri is the radius of the inner cylinder and Ro be the radius of the outer cylinder, and the fluid is between the inner cylinder and the outer cylinder. And let us say that this inner cylinder is rotating. It is rotating with an angular velocity omega, and so you have a fluid now between two cylinders. The inner cylinder is rotating, because of which the fluid outside will actually start moving. But because the outer cylinder is not rotating, the velocity of the fluid exactly on the outer surface or outer cylinder should be 0. And our idea is to find out how does the velocity change from the inner to the outer cylinder. Okay. So, the appropriate coordinate system that we want to consider here would be cylindrical coordinate system. Let us assume that the cylinders that you are looking at are really long, okay. So, much long in the z direction. So, the z direction is going to be perpendicular to the plane that we are considering, and the cylinders are so long that we can neglect all variations in the z directions, okay. So, and also the velocity in the z direction. So, because the inner cylinder is rotating, we would expect that the fluid flow is in the theta direction really. So, if I am taking the cylindrical coordinate system, I have an r which is in the direction of the radius, then I will have a theta direction which is in the plane, and then there is an z direction, and that is perpendicular to the plane. We will assume that Vz is equal to 0 and del by del z are also equal to 0, because the cylinder is infinitely long, okay, perpendicular to the surface. There is nothing that is going to change in that direction. If that is the case, then let us see how do the equations simplify. Okay. So, the first thing that we need to write down is the mass conservation equation. So, these are again standard equations that we need to take from a book. So, we have 1 over r del by del r of r v r plus 1 over r del by del theta of v theta plus del v z by del z is equal to 0. And as I said, you can take it from any standard textbook, because the equations would look a little different from the one which we write in Cartesian coordinate system. So again, you have r, theta and z direction. So there are three terms. One depends upon Vr, the second depends upon V theta, and the third depends upon Vz. Now, we need to simplify this equation. We know that we are assuming that the flow is purely azimuthal. That means it is only in the direction of theta. It's and the pipe is infinitely long. So, there is nothing that is changing in the z direction. So, we throw away the last term, del by del z of Vz is equal to 0. Now, also we are going to say that there is nothing that is going to change in the theta direction, because theta direction, if you look at, that is, the flow is just continuous. There is no theta that is different. So, theta equal to 0 or theta equal to pi by 4, it is just same. So, you would not expect anything that is changing in the theta direction, and therefore, derivatives of any quantity in the theta is also going to be 0. So, therefore, I can cancel out the second term, and that only leaves us with the first term, 1 over r del by del r of r V r is equal to 0. So, if you integrate it, you get r V r is a constant, or V r is equal to constant divided by r. Now, in order to evaluate this constant, we need to calculate what is that, what we need to have some physical insight. So, what should be, let us say, the value of V r on the surface of the inner cylinder. Let us imagine that is your inner cylinder, and this inner cylinder is rotating, in a counterclockwise fashion with some angular velocity. What do you expect the value of V r on the surface of the cylinder? You can't have fluid that is going into the cylinder, because the cylinder is a solid cylinder. So, V r on the surface of the cylinder has to be 0. So, we can impose that condition and say that at r is equal to Ri, the radius of the inner cylinder, V r is equal to 0, and that implies the constant is equal to 0, and that means V r has to be 0 everywhere in the fluid domain. So, now we have said, we have found that V r is 0 everywhere in the fluid domain. V z is equal to 0 because we have assumed an infinitely long pipe and there is no flow along the length of the pipe, and there is only fluid flow is in the theta direction, and therefore, we need to only worry about the theta component of the fluid velocity. We can write down only the theta momentum equation, but before that it is worth looking at the radial component of velocity, or r momentum equation as well, because that is going to give you some insight into the problem. So, we can look at theta momentum equation, that is what is going to give you information about the flow profile. So, let us start by doing that. We start by writing down the theta momentum equation, the unsteady term which is rho into dou v theta by dou t, and then we have the convective term which is v dot grad v theta plus 1 over r V r V theta. Again, you can look at this from any standard textbooks, and then you have the pressure gradient term which is minus 1 by rho dou p by dou theta, plus you can have the viscous term which is mu, the dynamic viscosity, times del square V theta minus V theta by r square plus 2 by r square dou V r by dou theta. So, that is the theta momentum equation. So, the quantities that are not needed, we have unsteady term, okay. We have v dot grad v theta, we need to check V r is 0, dou p by dou theta is 0, because we are assuming that del by del theta of any quantity is 0, and this is also 0. We need to further investigate what is grad v theta and what is del square v theta. So, again I look at standard textbooks and look at what is v dot grad v theta. V r into dou v theta by dou r plus 1 over r del v theta by del theta plus v z del v theta by del v theta. Now, if I look at V r is 0, by definition del by del theta of any quantity is 0 and we have V z equal to 0. In other words, V dot grad V theta is also for our system. We need to find out what is del square V theta now. Del square V theta, again I look at the standard textbooks and find out what is the equation for Laplacian in cylindrical coordinate system, and I find that that's equal to 1 over r del by del r of r del by del r of v theta plus 1 over r square del square v theta by del theta square plus del square v theta by del z square. So, by definition these two quantities are 0 because we have assumed that del by del thetas and del by del z's are 0. So, only that first term remains. So, we ended up, so we have this quantity which is essentially that now and that we have 1 over r del by del r of r del v theta by del r minus v theta by r square is equal to 0. So, that is what the theta momentum equation reduced to. We can look at what r momentum equation reduced to. Again I look at the equations and write dou v r by dou t plus v dot grad v r minus v theta square by r is equal to times rho is equal to minus dou p by dou r plus mu into del square v r minus v r by r square minus 2 by r square del v theta by del theta. So, that is the r momentum equation. Again let us throw away the terms that we do not want, unsteady. V r is equal to 0, we have already find, v theta is there, we do not know anything about dou p by dou r, v r is 0, v r is 0, del by del theta is 0. Means we ended up having that dou p by dou r equal to v theta square by r. Now, if you look at this equation carefully, the right hand side, okay, that is v square by r. So, that is not force, okay, or it is the centrifugal force density, the centrifugal force acting per unit mass, okay. So, that is equal to the pressure gradient. So, in other words, whenever the fluid elements are rotating, it experiences a centrifugal force and that force is actually balanced by a pressure gradient in the r direction. So, something is rotating in the theta direction, it experiences a centrifugal force and that force is exactly balanced by the pressure gradient. So, the radial pressure gradient balances the centrifugal force. Radial pressure gradient balances the centrifugal force. So, that is the information that you get the r momentum equation. The theta momentum equation of course gave you a differential equation which we need to solve and find out what is v. Solving it now. So, the equation let me write down again, 1 over r del by del r. So, we do not need to now write it as partials, it is total derivative d by dr of r dv theta by dr, ordinary derivatives, minus v theta by r square is equal to 0. I will do the differentiation, 1 over r into d square v theta by dr square plus derivative of r is 1 times dv theta by dr minus v theta by r square is equal to 0, or d square v theta by dr square plus dv theta by dr minus v theta by r square is equal to 0. So, that is the differential equation that we need to solve to calculate what is v theta. Now, these kind of differential equations, okay. So, d square y by dx square plus 1 by x dy plus y by x square is equal to 0. So, these equations are called Euler-Cauchy equations. And they admit a solution of a power law. Okay, for example, here the solutions that these equations will have will be something like r to the power of m. So, that is a kind of solution that we will have. So, we can actually try to find out what that would be. So, if you say that v theta is actually given by r to the power of m, then if you substitute d square v theta by dr square is m into m minus 1 into r to the power of m minus 2 plus 1 over r into m into dv theta by dr r to the power of m minus 1 minus v theta is r to the power of m by r square is equal to 0, right. So, if I cancel all r to the power of this, that and that, I have m into m minus 1 plus m minus 1 is equal to 0. So, that is m square minus m plus m minus 1 is equal to 0, m square minus 1 is equal to 0, or m is equal to plus or minus 1. That means, my solution is going to be v theta equal to c1 r to the power of 1 plus c2 r to the power of minus 1, or I will simply write it as c1 to the power r plus c2 divided by r, where I do not know what is c1 and c2. c1 and c2 are two integration constants which we need to calculate, and we can calculate it because we know the boundary conditions, right. We have an inner cylinder that is rotating with an angular velocity omega. We have an outer cylinder that is static. So, and the inner cylinder has a radius r(I), the outer cylinder has a radius r(O). So, we can say that at r is equal to r(O), v theta is equal to 0, at r is equal to r(I), v theta is equal to r(I) times omega. So, we have got two boundary conditions, we have got two unknowns. So, we can substitute and find that, so the first equation gives that 0 is equal to C1 RO plus C2 by RO. The second equation tells you that omega Ri is equal to C1 Ri plus C2 by Ri. So, we can rewrite this as 0 equal to C1 plus C2 by RO square. We can rewrite this as omega equal to C1 plus C2 by Ri square. So that's equation 1. This is equation 2. Subtracting, let's say 2 from 1, omega equal to C2 into 1 by Ri square minus 1 by Ro square. So that gives you C2 is equal to omega divided by 1 by Ri square minus 1 by Ro square. You can now go ahead and substitute, let's say, in the first equation, which says C1 is equal to minus C2 by Ro square. So that's equal to minus omega by Ro square into 1 by Ri square minus 1 by Ro square. And therefore, you are ready to get your expression for V theta. V theta is equal to C1 into R, that's minus omega by Ro square into 1 by Ri square minus 1 by Ro square times R plus C2 by R, which is omega by 1 by Ri square minus 1 by Ro square times 1 by times R. So if you want, you can rearrange that expression. You can do it yourself, and nicer way to represent it would be, it's just omega times Ri into Ro by Ri minus R by Ro by Ro by Ri minus Ri by Ro. Just rearranging that equation if you like. So that is the expression for the velocity profile between two concentric cylinders. In fact, if you plot it, if that was the inner cylinder and that was the outer cylinder, and if the inner cylinder is rotating, you will see that the velocity profile would, so the velocity at that point would be something of that sort, and then it should become 0 and it would decay like that. Has to plot it and see. Okay, but that's what the velocity profile is going to be. Let me just box that. That's the expression. You don't need to remember anything. It's just that that's the information that you get when you solve the cylindrical problem. It also tells you how you should deal with equations in cylindrical coordinate system, how some of the non-trivial terms contribute, and the pressure centrifugal force balance is the other thing that nicely came out of this analysis.